In this next video, I want to show you what to do when you see what looks like exponential growth when you see it in a table of data. So I've created two examples. These really are exponential growth situations. And what's unique about these two examples that I'm going to start with is that these are exactly exponential. I created them so that the data would have an exact scale factor. And I just want to show you how to find that scale factor if you don't happen to know what it is. Sometimes it's going to be obvious, sometimes it's not, and I want to give you the tools so that you can figure out exactly what to do when you have an idea that it's exponential, but you're not exactly sure how to write that equation. So let's look at this data on the left-hand side, this growth example. I created this as sort of a model for something that is growing exponentially. And you know, one of those ways that one of those examples of things that grow exponentially is mold on a piece of bread. And so if we're talking about, let's say, days for our x and the amount of mold growing on a bread, this might be an example of the way that that mold grows on a piece of bread. It's kind of gross. So what we want to try to figure out is, first of all, we look at this table and we say, well, it certainly doesn't seem to be linear. It goes up here by 9, and then it goes up by like 36. It's increasing. This amount that it's going up by is not going up by the same amount. That would be linear. That would be a constant rate. But rather, it seems to be going up by bigger and bigger and bigger amounts. And that's a really good hallmark of an exponential growth kind of a situation. What we want to know is, if this is exponential growth, then what we're doing is not adding the same amount, but we are going to be multiplying by the same amount. And the way to actually find out what that scale factor is actually pretty easy. If I think about this, I'm saying, okay, well, it's 3 times whatever that scale factor is. I'm going to use that b because we know that when we get the equation that models this, it's going to be a times b to the x. That's the way that exponential equations should look. And this is our scale factor here. So when I take this term 3, I multiply it by whatever that scale factor is, and that's how I got to 12. It's just I don't know what that scale factor is when I first look at this problem. But now I have a really easy Algebra 1, maybe even middle school kind of a problem here, where we say, okay, 3 times what equals 12? And I mean, it's pretty obvious by looking at it. But one way to think about this is, if we really just took this apart algebraically and we solved this for b, well, we would divide both sides by 3. And I'm actually going to write this, okay, this 3 cancels here. And what I get is that scale factor is 12 divided by 3. And so that's obviously that's equal to 4. But I think what I want you to really think about is this fraction here. This fraction, this way that I got this scale factor, is I took this term, 12, and then I divided it by the term in front of it. And we can actually do that with any of these terms. I can say, oh, well, this 192, let's see here, b, if this is really exponential and this is multiplying by that same amount each time, well, then that should be, let's see here, 192 divided by that term in front of it, 48. And I'll go ahead and grab a calculator here if I can find it. So here's my calculator, and I do, let's see here, 192 divided by 48, and sure enough, I get 4. I still get that same scale factor of 4. And so what we can see by this is the way that we can get this b in any exponential growth situation that's given to us in a table of data, as long as this is subsequent every single day, right? As long as this is giving us data so that I can see the exactly one day before it, then this scale factor should be this term 12 divided by that term in front of it, or indeed any term divided by that one in front of it. And so what we have here is our scale factor that we figured out for this one is 4. And now we already know, or we've already talked about, the fact that this beginning point, this starting point, that y-intercept where x equals 0, this is going to be our starting point, our A. And so if we put all that information together, what we can get is the equation that models this growth of this mold on this bread is that starting value 3 times that scale factor 4 to the x. Now, what's valuable about a model here is that we have data between 0 days and 10 days, but maybe what we want to know about is something that we haven't measured yet. A model allows us to essentially start to predict the future. We can say, well, if we assume that the growth is going to continue to go that way, if we use that to predict, and maybe that's a good assumption and maybe it's not. In the case of mold, this is a situation that's pretty well controlled. So we understand it pretty well. And so I think it's safe to assume that once we have that model, it's going to behave predictably because we know mold behaves predictably. And so this model should hold into the future. And so if I say, well, I want to know how much mold will there be at week, let's say 14. Well, then I'm going to say, well, my model now tells me I don't have to wait until the 14th week. I can say my model predicts that it'll be 3 times 4 to the 14th power. And we'll go ahead and put that into a calculator and calculate it out. The final value is not that important to us right now. The key finding for us here is when we want to know what that scale factor is, we take a term and divide it by the term in front of us. And if it is genuinely an exponential growth, that should be a constant scale factor all the way down our data. Now, this also works in the case where the data is decreasing. And so I've created an example here that has to do with money. Sometimes if we buy a piece of equipment, it has a value when we first buy it. So this is $1 million machine for a factory. And every year it depreciates. The value depreciates. Machines get old, they get less state of the art, and so the value of it goes down and down and down. Anybody who has bought a car knows that this is true. The value of machines depreciates. And I'm going to put that word down here just so that we can remember that word depreciate. Depreciate is a word that gives you a good indication that we're talking about a decay situation, and typically a depreciation would be an exponential decay kind of a situation. Now, what's interesting here is we know that if we're talking about exponential growth, it should be a times b to the x times b to the x. And so what we're doing is we're multiplying here by some value every time. But you might be looking at this and saying, well, wait a second, those numbers are getting smaller. So this might be thought of as dividing. And what I want you to do is I want you to sort of use this sort of magic information that we just got from this first example and actually just apply it here. And what we're going to find is that there really is a constant number that's being multiplied here. The only difference is that the number that we're going to get here is going to be something that is a less than 1. It's going to be a decimal. And so indeed, this trick that we learned was take this term, divide it by the term in front of it. So I'm going to take this term. This is 250,000. So I'm going to try to get this B up here. This is $250,000 divided by my original $1 million machine. And so this scale factor ends up being 0.25. And I think if you look at those numbers, if you take a minute and actually pause the video, you can do it yourself. Take each of these numbers and multiply it by 0.25, and you're going to get that next value. Now, one of the things that I want to point out in this example is that because we're talking about money, these decimals are okay. So multiplying down here and multiplying by 0.25, multiplying by 0.25 each time, it's okay that we're getting, 15.3. We're talking about $15.30. And this actually may have been cut off when I did this in Excel. This might have actually been $15.25, and it's just been rounded. In any case, this scale factor applies perfectly fine at exactly 0.25 all the way down. This is an exactly exponential decay situation, and I created that way so that I know that those numbers are going to work out that way. So just like in our first example, we take our starting point of $1 million. So 1 million, here comes all those zeros, times our scale factor of 0.25 or just 0.25 to the x. So this would be the equation that models the value of that machine. It looks like in 10 years it's only going to be worth $1. Depreciates pretty fast. And I think that's one of the things that is that's worth noticing here, that what we're really talking about is the remaining value. So while I've said this depreciates, it's not actually depreciating by 25%. It's down to 25% of the previous value. So it's actually depreciating by 75%. That would be a pretty steep depreciation rate. I would hope that a $1 million piece of equipment wouldn't depreciate quite that quickly. But in any case, this is an example that I made up. In any case, the reason that I bring up the detail on the exact value is because of what we're going to do next. So one of the things that you all noticed when we were doing the Skittles situation was that the values that you got were not exactly a scale factor, multiplied by a scale factor every single time. When you actually take the Skittles and you roll them out onto the table, certainly there's a 50% chance of that occurring, but it's a chance, it's probabilities. And so we, in the long term, if we did it a lot of times, then our average, probability would be that 50% rate of getting that Skittle to land S side up. And I will tell you that the data that I have in this example is not that 50%. I've actually chosen a different set of data because I don't want to do the math and take that away from you. I do want you guys to do that Skittle example, but this will be a good one to help you to understand the Skittle situation. So what I've got here again is data that it looks like, well, it's starting to go up and it's just going up by 1 each time. 2 plus 1 is 3, plus 1 is 4, plus 1 is 5. But then now it goes up by 2. Goes up to 7, goes up by 2, then it's going up by 3, then it's going up by 3, going up by 5, and 6, and 6. And so what's happening here is actually following a more of an exponential trend. And just to show you that, I did graph this using Desmos. And so I just wanted to pull that in and show you that what we have is that sort of characteristic curve where it's getting steeper and steeper and steeper. So when we see that data and we're convinced that this seems to be an exponential model, our next job is to try to figure out, well, what would our scale factor be? And so in this case, we have to do just a little bit more thinking. We know that what we've got to do is we've got to sort of think about what am I multiplying by each time? And we know that that scale factor is going to be this number divided by this number. And so here, what I've done is I've actually looked at this data and I found out that this, and let's go ahead and just copy this right in here. So this data here is what I get when I actually divide each term divided by that previous. And we'll be able to see that a little bit better. So I use the computer to do that work for me a little bit quicker here, but let's go ahead and just put these right in here and see if I can just sort of match that up so that you can kind of see. So this 1.5, not too bad. It's kind of matching up. Okay. So this 1.5 is what I get. We'll just sort of put that in there so we can see. This is what I get when I did 3 divided by 2. And here when I did 4 divided by 3. Again, I'm taking the next term, I'm dividing it by the term in front of it. So this one is what I got when I did 5 divided by 4. And so there's a little bit more calculation here. I did that for all of these terms divided by the term in front of it. And so, down here, this, I believe that this next one here, this one here goes from, so this one here is my 32 divided by 26. Now, what I noticed here is that the data doesn't seem to be exactly consistently the exact scale factor, but it does sort of look like it has an average scale factor. So an average B that's somewhere around 1.3. Now, I happen to know that it's around 1.3 because I created this data on purpose. And the key here is, what I want you to notice is that the process really is the same. We just have to sort of think about what is our model and what is our actual data. And so, again, I'm still going to write my model, and I'm going to say, okay, my starting point was 2, and my scale factor is this average. I'm going to use the average of all of those multiplying factors there to the x. Now, this is the time when we have to sort of think about what the difference is between a model equation and the actual data. If you plug in 1 and 2 and 3 and 4 into this model, you won't get these exact numbers, but you will get something that's really close. And that's really what a model is meant to do. It is not perfect, but it's close enough to help inform us about a trend and where we think the data is going. And so, ultimately, if we think about a real world example, if we think about predicting the spread of a disease, if we know that a disease is spreading at around, 30%, then we can use an exponential model like this to predict, but we can't say for sure, just like its probabilities, in the last example that we were talking about, we can't say for sure that the actual data is going to match that perfectly. But what we can say is this is the best model that we have to get us a close prediction. And that's the value of what models really do for us. So towards that end, I'll show you just one last thing, and then we'll close this out. I just want to show you how close our model turns out to be. So we have 2 times 1.3 to the x. And so if we go in here, here's the data that I just had, same data that I had on the last slide. And I'm just going to put in the equation here. So y equals 2 times 1.3 to the x. And what you see here indeed is we've got a graph that sort of follows that trend line pretty well. Is it exactly right? No. And in fact, we could probably tweak our model here now that we have an approximate value. And in fact, when we did our average, we didn't do 1.3. So maybe I need to put in that 1.32. And you can see now we're really a lot closer. In fact, this model, even though it didn't exactly predict these points in the middle, it was close. It's a little bit low predicting these values. It did predict this value at 10 weeks exactly right. And so the value of that model is that within a percent error, it allows us to predict the future. And so here, again, The key piece of information that we got here was to take the value and divide it by the value in front of it, the term in front of it, to get whatever that scale factor is. If that scale factor is not exact, but it seems to be sort of hovering close around an average, do that all the way through your data and take that average value. That average value can give you a pretty good model within a percent error. And that's the lesson for today.